Welcome to the lectures in data analytics. In this series of lectures, I am going to introduce to you model building. In particular, I will be talking about building linear models using techniques called regression techniques. So, let us start with some basic concepts. We are going to introduce the notion of correlation, different types of correlation coefficients that have been defined in the literature, what they are useful for. This is a preliminary check you can do before you start building models. Then I will talk about regression, specifically linear regression, and I will introduce the basic notions of regression and then take the case of two variables before taking going through multi-linear regression, where there are several input variables and one dependent output variable. Finally, after building the model, we would like to assess how well the model performs, how to validate some of the assumptions we have made, and so on. So, this is called model assessment and validation. So, let us first look at some measures of correlation. We have already seen one in the basic introductory lectures to statistics. So, let us consider n observations of two variables x and y. So, denoted by the samples xi comma yi, and we can of course compute the sample means. We have seen this in statistics, which is just the summation of all values divided by n for x, which is denoted by x bar, and similarly we can do the sample mean of y, which is denoted by y bar. We can also define sample variances, which is nothing but the sum squared deviation of the individual values from the respective means, xi minus x bar whole square, summed over all the values divided by n or n minus 1 as the case may be. So, we define these sample variances sxx and syy corresponding to the variance of sample variance of x and y. We can also define the cross covariance, which is denoted by sxy, which is nothing but the deviation of xi from x bar and the corresponding deviation of yi from y bar, and the product of this we take and sum over all values and divide by n. Notice again that this xi and yi are ordered pairs, in the sense that corresponding to the experimental condition ith experiment we have obtained values for x and y, and that is what we have to think. You can't shuffle these values any which way, they are assumed to be corresponding to some experimental conditions that you have set. So, there are n experimental observations you have made. Now, let us define what we call correlation. Correlation is nothing but indicates the strength of association between the two variables. Of course, if you find a strong correlation, it does not mean that the one variable is a cause and the other is an effect. You cannot treat correlation as a causation, because there can be a third variable which is basically triggering these two, and therefore, you can only find the correlation, but cannot assume that one of the variables is a cause and the other is an effect. We can also, before we actually do numerical computation, we can check whether there is an association between variables by using what is called the scatter plot. We have done this before. So, we can plot the values of xi on the x axis, yi on the y axis, and for each of these points, and we can see whether these points are oriented in any particular direction. For example, the figure on the left here indicates that the yi increases as xi increases. There seems to be a trend in this. In particular, we can say there is even a linear trend as xi increases, yi correspondingly increases in a linear fashion. This is a positive trend, because when xi increases, yi increases. In the next figure, the middle figure, we show a case where xi is, as xi increases, yi seems to decrease, and again there seems to be a pattern association between xi and yi, and this is a negative trend. Whereas, if you look at the third figure, the data that we find seems to be having no bearing on each other, that is yi values do not seem to depend in any particular manner on the xi values. When xi increases, maybe yi increases for some cases and yi decreases, that is why it is spread in all over the place. So, we can say there is little or no correlation. This is a qualitative way of looking at it. We can quantify this, and there are several measures that have been proposed depending on the type of variable and the kind of association you are looking for. So, let us look at the most common type of correlation, which is called the Pearson's correlation. Here, as we started with, we have n observations for the variables x and y, and we define the Pearson's correlation coefficient denoted by Rxy or sometimes denoted by rho xy by this quantity defined, where we are essentially taking same thing that we did before, the covariance between x and y divided by the standard deviation of x and the standard deviation of y. The numerator represents the covariance between x and y, can also be computed in this manner. We can expand that definition we have for the covariance, and we can find that it is nothing but the product of xi yi minus n times the mean of x and the mean of y, which represents the covariance of x and y, and the denominator represents the standard deviation. We can look at this division by the denominator as what is called normalization. So, this value is now bounded. We can show that Rxy will take any value between minus 1 and plus 1. Minus 1, if it takes a value, we say that the two variables are negatively correlated. If Rxy takes a value close to 1, we say they are positively correlated. On the other hand, if Rxy happens to a value close to 0, it indicates that x and y have no correlation between them. Now, how we can use this, we will see. So, this correlation, Pearson's correlation, actually is useful to indicate there is a linear dependency between x and y. For example, if y is a linear function of x, then the correlation coefficient or the Pearson's correlation coefficient will turn out to be either close to plus 1 or close to minus 1, depending on whether y is increasing with x, then we say it is a positive correlation, as we saw in a figure. If y is decreasing with x linearly, then we say it is negative, the correlation coefficient will be close to minus 1. On the other hand, if the correlation coefficient is close to 0, all we can conclude from then is perhaps there is no linear relationship between y and x, but perhaps there is non-linear association. So, we will come to that a little later. The way it is defined, we can also not apply it to ordinal variables, which means ranked variables. So, suppose you have a variable where you have indicated your scale on a scale of say 0 to 10, okay, let us say the course. Those kind of variables are typically you do not apply Pearson's correlation. There are other kinds of correlation coefficients defined for what we call ranked or ordered variable, ordinal variables. Typically, in order to get a good estimate of the correlation coefficient between y and x, you need at least 20-30 points, okay, that is generally recommended. And then like your sample mean or the sample variance, standard deviation, if there are outliers, if there is one bad data point or experimentally experimental point which is wrongly recorded, for example, that can lead to misleading values of this correlation coefficient. So, it is not robust with respect to outliers, just like the sample mean and sample variance we saw earlier. So, let us look at some examples. This is a very famous data set called the Anscombe's data set. Here there are 11 data points. For each of this, there are 4 data sets, I have only shown 3 of them. Each of them contains exactly 11 data points corresponding to xi and yi. These points have been carefully selected. In the first one, if you look at it, if you plot the scatter plot, you will see that there seems to be a linear relationship between y and x in the first data. In the second data, if you look at this figure, you can conclude that there is a non-linear relationship between x and y. And the third one, you can say, well, there is a perfect linear relationship for all the data points except one which seems to be an outlier, which is indicated to be far away from that line. So, if I apply Pearson's compute Pearson's correlation coefficient for each of these data sets, we find that it is identical. It does not matter whether if you actually apply it to first data set or second data set or third data set. In fact, the fourth data set has no relationship between x and y, and it turns out to be they have the same correlation coefficient. So, what it seems to indicate is that if we apply the Pearson's correlation and we find a high correlation coefficient close to 1 in this case, it does not immediately, you can't conclude there is a linear relationship. For example, this is a non-linear relationship and still gives rise to a high value. So, it is not confirmatory in the sense there is a linear. We can say it is one way. If there is a linear relationship between x and y, then the correlation Pearson's correlation coefficient will be high. When I say high, it can be minus 1 or plus 1, but if there is a non-linear relationship between x and y, it may be high or it may be low. We will see some data sets to actually show this, illustrate this point. Here are 3 examples. In the first example, I have taken 125 equally spaced values between 0 and 2 pi for x, and I have actually computed y as cos of x. So, there is a relationship between y and x, in this case is a sinusoidal relationship. So, if we apply the Pearson's correlation coefficient, compute the Pearson correlation coefficient for this data set, we get a very low value, close to 0, indicating as if there is no association between x and y, but clearly there is a relationship because it is non-linear. In fact, it is symmetric. The points above the 0 line, when it is x is between 0 and pi by 2, and when it is between pi by 2 and pi, and between pi and 3 pi by 2, 3 pi by 2 and 2 pi, they all seem to cancel each other out and finally give you a correlation coefficient which is very small. Does not imply that there is no relationship between y. All you can conclude from this is perhaps there is no linear relationship between x and y. Similarly, let us look at another case where there is non-linear y is equal to x squared, where I have chosen x between 0 and 20 with equally spaced point of 0.5 each, 40 points you get, and I have computed y equals x squared, and then computed Pearson's correlation for this xy data. You find it is a very high correlation coefficient. You can't immediately conclude there is a linear relationship between x and y. Okay, you can only say there is a relationship, perhaps it is linear, maybe it is even non-linear, we have to explore further. If it is close to 0, I would have said there is no linear relationship, okay, but it is in this case it is very high. So, there is some association, but perhaps the association you can't definitely conclude it is linear, it may be non-linear. On the other hand, if the data, if I had chosen my x data between -10 and 10 symmetrically, okay, for between -10 and 0 y equals x squared will have positive values, between 0 and 10 y equals x squared will have positive values again, although x is positive, y is positive in this range, and between negative values for x, y is still positive. So, these will cancel each other out exactly and will turn out that the correlation coefficient in this case is 0, although there is a non-linear relationship between y and x. So, all we are saying is this: if there exists a linear relationship between y and x, then the Pearson's correlation coefficient will be either close to 1 or -1, perfect relationship, linear relationship. On the other hand, if it is close to 0, you cannot dismiss a relationship between y and x. Similarly, if value is high, looking at just the value, we can conclude that there definitely exists a linear relationship between y and x. You can only say there exists a relationship between y and x. So, let us actually look at other correlation coefficients. You should note that Pearson's correlation coefficient can be applied only to what we call not ranked variables, ordinal variables, real valued variables like we have here. So, let us look at other correlation coefficients that can be applied even to ordinal variables. Now, here is a case where we only look at look for degree of association between two variables, but this time the relationship may be either linear or non-linear. If x increases, y increases or decreases monotonically, then the Spearman's rank correlation will tend to be very high. So, here is a case when x increases, y increases. This also is a case when x increases, y increases monotonically, but in this case the right hand figure is a non-linear relationship, the left hand figure indicates a linear relationship. Let us apply define Spearman's rank correlation, apply it to the same data set and see what happens. So, in the Spearman's rank correlation, what we do is convert the data, even if it is real valued data, to what we call ranks. So, for example, let us say I have 10 data points, in this case xi is like somebody has taken a scale between, let us say 2 and 10, 1 and 10, and similarly y is also a value between 1 and 10. So, what we have done is looked at all the individual values of x and assigned a rank to it. For example, the lowest value in this case x value is 2 and it is given a rank 1. The next highest x value is 3 and that is given a rank 2, and so on and so forth. So, we have ranked all of these points. Notice that the 6th and the first value both are tied. So, they get the rank 6 and 7, which is the midway, the half of it. So, we have given it a rank of 6.5 because there is a tie. Similarly, if there are more than 2 values which are tied, we take all these ranks and average them by the number of data points which have equal values, and correspondingly we obtain the rank. We also rank the corresponding y values. For example, in this case the 10th value has a rank 1 and so on so forth, 8th value has a rank 2 and so on. So, we have given a rank in a similar manner. Now, once you have got the rank, you compute the difference in the ranks. So, in this case the difference in the rank for the first data point is 2 and we square it. Similarly, we take the difference in the second data point in the ranks between xi and yi, which is 2, and square it and we get 4. So, like this we take the difference in the ranks, square it, and we get the final what we call the d squared values. We sum over all values and then we compute this coefficient. It turns out that this coefficient also will be lie between -1 and +1, and -1 indicating a negative association and +1 indicating a positive association between the variables, and in this particular case the rank the Spearman rank correlation turns out to be 0.88. Let us look at some of the things. As I said, 0 means no association. When there is a positive association between y and x, then the RS value or Spearman's thing will be +1, like the Pearson's correlation, and similarly when y decreases with x, then we say that the Spearman's rank correlation is likely to be close to -1 and so on. Okay. The differences between Pearson's and Spearman is not only can it be applied to ordinal variables, even if there is a nonlinear relationship between y and x, the Spearman rank correlation can be high. Okay. It is not likely to be 0, it will have a reasonably high value. So, that can be used to distinguish, maybe to look for the kind of relationship between y and x. So, let us apply it to the Anscombe data set. In this case also we find that for the first one the Spearman rank correlation is quite high, in the second one also reasonably high. In fact, the Pearson also was high. Notice that the Pearson was same for all this, and the third one also is fairly high, 0.99. So, all of these things it is indicating that there is a really strong association between x and y. Suppose we had applied, I would suggest that you apply it to the cos x example and y squared x is equal to y squared example. You will find that the Spearman rank correlation for these will be reasonably high. It may not be close to 1, but it will be high, indicating there is some kind of a nonlinear relationship between them, even though Pearson's correlation might be low. So, a third type of correlation coefficient that is used for ordinal variables is called the Kendall's rank correlation, and this correlation coefficient also measures the association between ordinal variables. In this case, what we define is a concordant and a discordant pair. If you look at the values, compare two observations, let us say x1 y1, and sorry, here it should be x1 y1 and x2 y2. If x1 is greater than x2 and the corresponding y1 is greater than y2, then we say it is a concordant pair. That means, if x increases and y also correspondingly increases, then these two data points are said to be concordant. Similarly, if x decreases, if x1 is less than x2, I am sorry, x is increasing, so x1 less than x2, and correspondingly y1 is less than y2, then also we say it is a concordant pair. That means, when x increases y increases, or x decreases and y decreases, then we say these two data pairs are concordant. On the other hand, if there is an opposite kind of relationship, so if you take two data points x1 y1 and x2 y2, and we say that we look at the data points and find that if x1 is greater than x2, but the corresponding y1 is less than y2, or if x1 is less than x2 but y1 is greater than y2, then we say it is a discordant pair. So, we take every pair of observations in a sample and then assign whether there is a concordant or discordant pair. Let us take an example and look at it. So, once we have the number of concordant pairs and number of discordant pairs, we take the difference between them, divide by the n into n minus 1 by 2, and that is called the Kendall's tau. We can take a item here, there are about 7 observations, let us say 7 different wines or tea or coffee, and there are 2 experts who rank the taste of the tea or coffee or wine on a scale between 1 to 10. For the first, the expert number 1 gives it a rank of 1 and expert 2 also ranks it 1. For the second one, the expert 1 ranks it 2, while the expert 2 ranks it in a scale or gives it a value of 3, and so on so forth for the 7 different types of thing. Now, you compare data point 1 and data point 2. In this case, expert's opinion is that 2 is, let us say, better than 1, expert 2 also says 2 is better than 1. So, it is a concordant pair. So, 1 and 2 are concordant, that is what is indicated here. Similarly, if I look at the data point 1 and 3, expert 1 says it is better, 3 is better than 1, expert 2 also says 3 is better than 1. So, it is a concordant pair. Similarly, if you look at 2 and 3, both are in agreement, 3 is better than 2, 3 is better than 2. So, it is a concordant. Let us look at the fourth and the first one. It looks like expert 1 says it is better, expert 2 also says better, concordant. But the second and fourth, if you compare, expert 1 says it is better, fourth one is better than the second, but expert 2 disagrees, he says the fourth thing is worse than the second one. So, there is a discordant pair of data, that is indicated by 2. So, 4 and 2 are discordant, 4 and 3 are discordant. Similarly, here it says 5 and 1 are concordant, 5, 2 are concordant, and so on and so forth. So, between every pair n into n minus 1 by 2 pairs you will get, and we have classified all of these pairs as either concordant or discordant, and we find there are 6 discordant pairs and 15 concordant pairs, and we can compute the Kendall's tau coefficient. Okay. This basically says if this is high, then there is broad agreement between the two experts, right. So, basically we are saying y and x are associated with each other, or so there is a strong association, otherwise it is not strongly associated, or completely, if the expert 2 completely disagrees with expert 1, you might get even negative values. Okay. So, the high negative value or high positive value indicates that the two variables x and y in this case are associated with each other. Again, this can be used for ordinal variables because it can work with ranked values here, as we have seen in this. So, again if we apply it to Kendall's rank to the Anscombe data set, we find that although it has decreased for this linear case, the value has decreased as compared to the Pearson and Spearman's correlation coefficient, it still has a reasonably high value. High in this case, typically you should, in experimental data you cannot expect to get a value I mean beyond 6.6 or 0.7, you should consider yourself fortunate typically, because we rarely know the nature of the relationship between variables, we are only trying to model them. So, in this case nonlinear relationship, you find again a reasonably high correlation coefficient for Kendall's rank, and the last one again it is linear, perfectly linear. So, you are getting very high association between them. So, really speaking, you can actually use these to get a preliminary idea before you even build the model. Of course, for 2 variables it is easy, you can plot it, you can compute these correlation coefficient and try to get a preliminary assessment regarding the type of association that is likely to be, and then go ahead and choose the type of models you want to build. And this is the first thing that we will do before we jump into linear regression. So, see you next class about how to build the linear regression model. Thank you.